I don't need a microphone, do I? I need a microphone? Usually I don't need. Do you hear me? Okay, so that's very good. Because I intend to tell you very interesting things. So you have to hear everything. Should wear this?
Maybe that you have to wear the microphone for the recording.
Ah, for the recording? Okay, good.
Yes.
Okay. So it will be even more interesting.
You put it lower, I guess. And
Yes.
this is for the camera.
Is it possible to, is it okay? But it's perhaps too strong to shift it down?
You can shift the microphone down.
Like this?
You get a golden medal.
Gold medal. Great, thank you. Okay. So first of all, to take 1 minute until everybody comes back from coffee, I wish to thank the organizers to invite me here. It's my first time in Brazil. And I'm coming from a country, a very, very tiny country, whose whole population is about 1/4 of population of São Paulo, something like this. So just to give you orders of magnitude. So I'm coming from Technion, Israel Institute of Technology. And again, it's really very nice to discover Brazil and São Paulo. So I must confess something at the outright of my talks, is that I'm a condensed matter physics in disguise, which means I'm not really doing a lot of atoms, and so I must confess it. Are there people doing condensed matter physics here? No, don't be ashamed. It's fine. It's very good. Yes, so, okay, good. Now, but I will say a lot of things about atoms and interaction between atoms and photons, don't worry. But I would like to give you some overview of interesting effects in physics. In fact, those effects are common to condensed matter physics, where it was initiated. It's called the Mesoscopic Physics. But as Philip said at the very beginning of his talk, a lot of the experiments, the concepts that were built for quantum mesoscopic physics, in fact, find their way in atomic physics, and more precisely, interaction between photons and atoms. But I will not enter there. I will stay, at least for the first lecture, at a very general level, and just we will entertain ourselves talking about physics. Is it okay with you? So tomorrow, it will be more down to the earth, with more heavy things. But today, just, enjoy, listen to the physics, and ask questions. Okay, fine? So, first of all what I'm going to say, no, not all. Today and tomorrow, what I'm going to say is basically taken from a book that I wrote a few years ago with my colleague Gilles Montambeau from Orsay University. And this is called Mesoscopic Physics of Electrons and Photons. So I retrieved the word electrons in order to keep only photons, but the idea, you understood what I wanted to say. Okay, so this is a relevant reference for what I'm going to say. So today in the part one, I will really introduce the field of mesoscopic physics. By the way, there are some of you heard this topic, quantum mesoscopic physics? Who heard this already? Who never heard about this topic? Beautiful, this is what I like. Okay. So it's an extremely rich topic at the end of the 90s. I think we can fairly say that perhaps close to 20% of the whole physics literature was devoted to this subject. And this just tells that things are, going up and down. So never be too, to think about yourself that you are changing the world. You see new generation, they say, well, we never heard about this, and we feel very good with this. Okay, but again, as very often in physics, the concepts are coming up and down, and so this, again, today is extremely useful, but in other fields. So introduction to mesoscopic physics. First of all, I will tell you about the Aharonov-Bohm effect. So who heard about the Aharonov-Bohm effect? So therefore, you did mesoscopic physics, because this is really at the heart of mesoscopic physics. Mesoscopic physics is the Aharonov-Bohm effect, and I will dwell quite a lot in this, okay? Okay, then I will tell you about phase coherence in quantum systems and effect of disorder. Okay, then I will present another very important effect in physics that is called the Charvin and Charvin effect, and about coherent backscattering. Who heard about Charvin and Charvin effect? Aharonov-Bohm, yes, but Charvin, no. This is because it was in Soviet Union at that time, I guess so. And who heard about coherent backscattering? Good, I'm happy, little bit. But it's the same. By the way, one is for electrons, one is for waves. And then I will pursue with discussing this phase coherence and self-averaging, something that is called universal conductance, universal fluctuations. And notion of classical probability and quantum crossings. But everything will remain at a very qualitative level today, okay? So the framework, we are going to be busy with something that is called multiple scattering of waves. Did you hear about multiple scattering of waves? If you didn't hear or you are not really sure about what it means, this is the idea. This is, so what I represent here with those circles are scatterers. Those scatterers, they can be whatever you want. They can be atoms. They can be atoms at resonance. It can be strontium even. They can be whatever you want. And those, but it can be also proteins of milk. It's the same idea. Okay? It can be impurities in metals, but they scatter. And then you send a wave, a plane wave, and this is the container of those scatterers, and the plane wave scatters from those scatterers and goes out. So this picture, you heard it. This is called single scattering. So you do it in quantum mechanics, you do it in wave mechanics, okay? And you calculate scattering cross-section, and you are very good at this, but this is not what I'm interested in. I'm interested in a situation where before the wave emerges, it goes through billions of scattering, not 2 or 3 or 4. For 2 or 3 or 4, I don't know how to solve the problem. It's very difficult. But if there is a billion of scattering events, then I know to say something, okay? So this is, we will never be interested in this. We will be interested only in that situation. Again, you have a set of scatterers that can be atoms, and you have photons on these atoms, and they scatter many, 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 many times before they emerge from the system, okay? This many is essential, okay? So to describe this problem, you need, in fact, basically only two characteristic lengths. One length is called the wavelength of the wave that scatters, that answers in the system. And you see what I told you, that I'm a condensed matter physicist. I wrote lambda f. Lambda f, it means Fermi wavelengths. Because, I cannot avoid this. In condensed matter physics, everything is Fermi velocity, Fermi wavelengths. So, but this is just the wavelengths. And the second characteristic length is called the elastic mean-free path, which is the scattering length inside the system. So this elastic mean-free path describes what is the scattering properties of your system. It depends on the density of scatterers, but more importantly, it depends on the scattering cross-section. This scattering cross-section can be extremely big, or it can be extremely small. So which means that the elastic mean-free path can be very large or very small, okay? And, but we know to calculate it. We will not worry about this today. And we will be in a limit where those two characteristic lengths are such that the wavelength is much smaller than the elastic mean-free path. And this is called weak disorder or weak scattering system. Okay? Did you hear about the notion of Anderson localization transition? Who heard about this? And you didn't hear about mesoscopic physics? This is exactly the same problem, okay? So Anderson localization transition is this problem, but when the wavelength becomes of the order of the elastic mean-free path. Then there is something that happens that for this value of disorder, you have to change the strength of the disorder in order to decrease this elastic mean-free path. And when you decrease it to be of the order of the wavelength, then something sudden appears in your system. It's a phase transition, and it's called the quantum phase transition because there is absolutely no temperature in this problem. And at this value of the disorder, which is a critical value of disorder, in 3 dimensions, you get that all the solutions of the Schrödinger equation or the wave equation or your favorite equation becomes exponentially localized. Okay, so this is this Anderson transition. And here, mesoscopic physics is just the limit of weak disorder, which means when we are far away from Anderson transition. But then we can go closer and closer. We still do mesoscopic physics, but then when it is Anderson, we call it Anderson. That's it. Okay, so now this is the framework. The framework will be always working with these waves and multiple scattering. And now the effect, the important effect, the relevant effect, which is, I would call it a canonical mesoscopic effect, which is the Aronoff-Bohm effect. So the Aronoff-Bohm effect, it's from 2 physicists, David Bohm and Yakir Aronov, and I'm very happy to also to discuss this effect because this was discovered in my university at the Technion when Yakir Aronov was a PhD student and Bohm was his advisor, and this was in 1959. And this was much before mesoscopic physics. Okay? But the idea of Aronoff-Bohm effect is a generalization of the Young two-slit experiment. And so somebody can tell me why it is so important, this Aronoff-Bohm effect? Because if it is just two-slit experiment, it was known before. So what is the bottom line of Aronoff-Bohm effect? Why is it important? In 2 words or 1 sentence? Huh? Interference, but interference I can have it also without. With this two-slit experiment, I have interference. But it was in order to emphasize something, which was the fact that okay, something, yes. Okay, so the idea was that in classical physics, you know that what has an importance, what can be measured are the fields, which which is the electric field, or the magnetic field. You can express the fields using potentials, for instance, the vector potential. But those potentials, they can be modified because of gauges. You can use different gauges in order to get the same field. And therefore, those potentials are helpful mathematically, but they don't have a reality. In quantum mechanics, this is not so. In quantum mechanics, in fact, you can see an effect of the vector potential directly. Okay? So how does it work? So here is the idea. You use this, here you have charged particles, say electrons, okay? And there is no multiple scattering. And in this two-slit experiment, you look at the interference picture on this screen there. You measure the intensity, which is the square of the wave function of the electron. Now, you know that it's quantum mechanics that you will see an interference picture on the screen, right? Without anything, without any Lorentz force and the field, without this. You see an interference picture, right? Now, what I'm doing is to insert in the middle here an infinitely long and thin solenoid, which means a magnetic flux, such that the rotor of this vector potential is zero everywhere. So there is no magnetic field, which means that the electrons that are going through all those trajectories, whatever trajectory you can draw, they will not feel any magnetic field. So there is no Lorentz force on them, right? And question, do you see a modification of the interference pattern due to this flux that is here? And the answer is yes, you see. And this is the essence of Aharonov-Bohm effect, that although there is no magnetic field where are the electrons, they don't see any magnetic field, they feel the effect of vector potential. Okay? So let's do it together. You can, in order to calculate the intensity here, you have first to calculate the two amplitudes of this path and of that path. And the two amplitudes, they have a strength and they have a phase. And the two phases which are associated to those two trajectories, they are given by those two expressions, where delta 1, 0 is the dephasing that you would have without this solenoid, without this term. Okay, it exists, it is something. And there is an additional term, which is just the circulation of the vector potential along this trajectory, okay? And in units, because this is what I have in the Hamiltonian, of E divided by H bar. Second phase, the phase associated to this trajectory, is some unknown and non-interesting delta 2 of 0, and the part that comes from circulation of the vector potential on the other path. And like this, you calculate the intensity on the screen, and what you obtain is this. The intensity we know from basic quantum mechanics. It's the sum of the amplitudes squared, okay? So this is what it is. And then if you expand this, you get this expression, which is the sum of the two amplitudes for the two paths, and an interference term, which is this one. Okay? Then I can rearrange all this. A1 squared, I call it intensity I1. This is intensity I2. And this is just this interference term, which oscillates with the phase difference between the two trajectories, delta 1 minus delta 2. And the phase difference, delta 1 minus delta 2, is in fact modulated by the magnetic flux. Why? Because delta 1 minus delta 2 depends on the flux. Okay? So therefore, you see that, so this is this. Okay, does it work? Yes, it's me that doesn't work. This phase difference is this, which we don't know what it is, but the two circulation of A is now the circulation over the closed path, which is the two amplitudes, and this is just the flux that is enclosed in this trajectory, and this is phi in units of phi 0 because of this E divided by H bar that we had. So you see that there is a continuous change of the state of interference. By changing phi, I change this delta delta, which means that I change the intensity as a function of flux. And this is, again, the essence of Aronoff-Bohm effect. You are with me? This was simple. This was very simple. This was too simple, perhaps. No, because it will change. Don't worry. Okay? Okay, so you are with me? So we know that there is this effect. So now I want to implement this idea in metals. And in metals, I claim that the analog of this intensity that we just discussed now is the conductance, electrical conductance. Everybody knows what is an electrical conductance? Everybody knows what is the Drude theory for transport in metals? Yes? Good. This is the only thing you need. Okay, so now the idea was the following. Instead of having this setup, you take, so this is a conductor, and this conductor is such that it is an annulus, it is a ring, and this ring is pierced by this solenoid that we had before. The same idea that we have an infinitely long magnetic flux, and now this is a pointer that doesn't work. You have so now here you have the electrons that go in the metal, and you see that, so all the points here are scatterers. So now we are in this multiple scattering business because we know that, so we know all of us because we know what is Drude formula. We know that in a metal, free electrons, for instance, if there are no impurities, then the conductance is infinite. And in order to have finite conductance, we need something to scatter the electrons. Okay? So this is why we are precisely in the framework that I defined previously. So we have those electrons that they scatter many, many times, billions of times, and they can go like this, they can go like that, they can do whatever you want. And again, there is this mean free path, and the wavelength is the Fermi wavelength. Okay, and now the point is that you ask, does the conductance depend on the magnetic flux? And the answer that was provided by Richard Webb in the 80s of the previous century was that the measurement was that indeed there is a dependence of the conductance as a function of flux. So what you see here, so this is this ring that he used, and what you see here is the conductance as a function of the flux. And what you see here is the Fourier transform of this conductance. And the Fourier transform has a peak at here, you see, and this peak corresponds to a flux that is just this phi 0 that we saw before. Okay? So there is a dependence of the conductance on the applied magnetic flux. So it is Aronoff-Bohm effect for disordered metals. You are with me? Did you fall from your chair? No, but you should. Because if I'm taking, a ring that way, big ring with, copper wires and all this, I put a magnetic field that way, the way you want, you will never see anything like this. The ring was small, extremely small. If I take a big ring, I have a conductance, I have everything, but there is no such dependence on the flux. So something happens, okay? And this is the whole idea of mesoscopic physics. Why do we see something like this? It's extremely strange. You should yell at me. You should say, this is not true. You are working at us. This cannot be true. This was a bad interpretation. Those guys did not understand anything about what they measured because this is not possible. Again, try to do it in your lab. This, you will not succeed. Okay. So, Webb et al., the conductance behaves that way. So you have a conductance that it's exactly the same as the expression that I showed for Aronoff-Bohm two-Young slit. There is a conductance that is just set up due to the disorder, and there is this modulation by the flux that is here. And again, if this is true, and it was true, it's a measurement, then we should reconsider the Drude theory, because according to Drude theory, this is not possible. And we like Drude theory. We even love Drude theory. So then there is something that we're missing. Okay, very good. And what we are missing is this idea of phase coherence and effect of disorder. So the Webb experiment has been realized on a ring of size about 1 micron. And at that time, it was very difficult to have this technology to do something like this. And just what I said before, if you have a macroscopic normal metal, so you scale up all what I said at larger scales, all those coherent effects, this Aronoff-Bohm effect, is washed out completely. Okay, you will never see it. And this means that it must exist a characteristic length, L phi, that is called the phase coherent length, beyond which all coherent effects disappear. Okay? And you agree with me? Should be something like this, because I see it for small systems, I don't see it for big systems, the same one. And mesoscopic physics is all about this L phi, and what is L phi? Is it kilometers? Is it micrometers? How to calculate it, and how to get a description of it. And the bad news is that until today, people in condensed matter physics, people in atomic physics, people in many other branches try to characterize and to measure and to define L phi, and nobody succeeded. Okay, so this is the challenge for you. Okay, what is L phi? Okay, so the vanishing of quantum coherence, if I ask you, what do you think could be the source of this vanishing of quantum coherence? You could say that it is related to some incoherent and irreversible processes that occur in your system of electrons that is coupled to the surrounding. Okay? So if you have zero temperature electrons, for instance, in a metal, they are fully coherent, right? In a metal, T equal to 0, it's not superconducting, nothing, just zero temperature, the system is fully coherent. You describe the wave function of Avogadro number of electrons using, Slater determinant, whatever, everything is coherent, right? So, but those electrons, you can couple them in a metal to other excitations. For instance, due to the thermal excitations of the solid, the phonons. You know what are phonons? By the way, how many people are PhD students and master students? How many are PhD students here? So you know all this very well, so this is boring. Okay, so very good. So you know what are phonons. So those electrons can be coupled to phonons. And in that case, precisely as Philippe said, but in another context, and you asked the question, it is not possible to have a complex valued energy. But of course it is possible. It is not even possible. It must be that way. And this describes precisely the decoherence. The broadening of the energy levels is decoherence, and phonons are like this, okay? So this is a source of decoherence, okay? Spontaneous emission is a source of decoherence also, okay? All these are sources of decoherence, but in condensed matter physics, we have phonons for this. Your electrons, they can be coupled to dynamical systems which are chaotic. So I heard that you, I mean, did you hear, do you know this book of Feynman, Lecture Notes in Physics? So he discusses this this LC chain of quadrupoles. You know about this? Did you? So this is an example of a chaotic dynamical systems. If you want to know more about this, come to me afterwards. Don't ask now, because just to trigger your appetite for this. It can be due to electron-electron interactions. And what I said before, the understanding of decoherence is difficult. It is a great challenge in quantum mesoscopic physics, which is unsolved so far. And the phase coherent length, L phi, accounts in a generic way for decoherence processes. Okay? So there is such a length, L phi. And in order to observe the coherent effect that I was discussing before, you must be in a situation where the size of the system is much smaller than this L phi. Okay? So we don't know what is L phi. We know that it exists. But if you want to see Aronoff-Bohm effect in metallic rings, you must be like this. So this depends on temperature. This depends on many things. Good. Now that we settled this question, what is the role of elastic disorder? So you remember our framework is that we have waves that do many scattering before emerging. And you may think that disorder erases phase coherence. Do you think so? Who doesn't believe that disorder erases phase coherence? Who believes that it erased phase coherence? Who doesn't believe anything? Most of them. Okay, so.
Just to see if I follow. There is no formal definition of coherence length.
Of the phase coherence length?
It is just when you observe this effect or not.
No, yeah, okay. I'm a little bit, how to say, provocative. What the bottom line is that we don't have a real good understanding of L phi is true. But we have situations where we know how to calculate and to say what will be L phi. But this perhaps, at the end, I will discuss this.
At the moment is only when you observe
yes.
the size of
there
the
is
system, the distance which you observe.
Yes.
That a Random-Bohm effect.
The only thing now that I want you to take home message is that there is such a length, and if the size of the system is smaller than L phi, you will observe all those phase coherence effects. If not, you will not observe them. But this is a quantum length, inherently. Okay, so again, you could tell me, but disorder does this for you. And for those that do not believe so, I will show you that this is indeed the case. So you remember that all the disorder that we consider is elastic disorder. And the phase coherence that we saw in this Webb experiment, in fact, was obtained for a given realization of disorder. There is one ring with, given scatters, impurities, and it's one realization, right? Now, if instead of having one configuration of disorder, you now average over disorder, you should see the vanishing of the Aronoff-Bohm effect. So this is a subtle point, what I'm going to say. It looks trivial. It really looks trivial, but it is very subtle. What I'm saying is that if you take a conductor, so suppose that this is a copper wire, okay, this length. It can be also this length. And I measure the resistance of this segment of this good metal. And I measure the resistance or the conductance of this segment, or a segment measured at Amsterdam University where York is working, or in San Carlos, do I measure the same thing, the same conductance? What is your answer? Yes or no? Who is in favor of yes? It is yes, because if not, it would be a problem, okay? We measure always the same conductance. Why so? Because we do not, those systems are so big that what we measure is the average conductance, and there are no fluctuations for such systems. And therefore, as we learned from Drude theory and all this, we measure always average with zero fluctuations, okay? And this is very good because therefore we can use those copper wires in order to do other things. So in principle, if I average over disorder, I should see always the same, okay? But if I average over disorder, I may lose those coherent effects. So let's see that it is the case. And I claim that this is the case because what we saw earlier is that the conductance of the Webb experiment is given by this expression. And if you remember, this dephasing here was, I said that this is something that is due to inherent disorder that is there, the multiple scattering. If I average over disorder, then this cosine of this that fluctuates will be zero, and therefore G of phi on average over disorder will be just this J0. Okay? So therefore all phase coherence effects, Aronoff-Bohm effect, is washed out when I average over disorder. So there is no effect. So what I saw is something for a given configuration because it's a very, very small ring, but if not, I lose those phase coherents. They are washed out. Okay? So disorder seems to erase coherent effects. So therefore they saw it. So what? It was just one realization. Okay, so this is where we stand. Everything is crystal clear. You're sure? Yes. Is it in the thermodynamic limit? So I don't know what you mean by thermodynamic limit, but the whole idea that we said before is that there exists a phase coherent length such as the size of the system should be smaller than this L phi. So we can never be in the thermodynamic limit that L goes to infinity because it has to be smaller than L phi. But L phi can be Earth-Moon distance. And therefore, L could be large enough, like in this wire that I showed, because in this wire, when we say that this and this have the same conductance, this is thermodynamic limit. Okay? So if the phase coherence length is that big, then I should see fluctuations for those resistances. There is a finite density of scatterers. Yeah, this is always. You remember what my first slide of the framework? If there is only 1 or 2 or 100 scatters, I'm not happy. I want a density of scatterers, which means that if you have a big system, you have really a lot of scatterers. Finite density. Yes, absolutely. Yeah.
When you say averaging over disorder, you mean different experiments or the same experiments, different realizations?
This is a very good question, but I don't want to answer now. It's okay, but it's a very good question. Keep it this question for later on. Okay? It is very, very good. Okay, so disorder seems to raise coherent effects. Now I want to formulate the same question, but to leave for a while metals and electrons and to go to optics and waves. Okay? Just to formulate the same question, but in another framework, because I told you that, we are doing photons, electrons, all the same. So I want to discuss the notion of Speckle patterns in optics. So suppose now that you have this disordered system. So this is a scattering system. Those are atoms, for instance, the atoms that Philippe is describing to us now. And I have light that is incident on a slab with many, many atoms that scatter those photons. And I want to know, when I measure the intensity on a screen outside, what do I see? So those scatters are just frozen. They are fixed. They have one given realization. So what do I see on a screen far away? I see what is called the Speckle pattern. This is the title of the slide. And this Speckle pattern looks like that. So this is a measurement. This is not numerics or theory. It's the outgoing light, the light here, builds a speckle pattern. And this speckle pattern is an interference picture. So the fact that you have a lot of scatterers like this, it's one given realization. What you see is an interference picture. This is an interference picture. The color code here is that when it is black, interference is destructive. When it is red, interference is constructive. And you have all the possibilities in between. So it's a fully interference picture. So, and this is a disordered system, right? But this is one realization. Again, everything is frozen, and this is what you observe. This is what you observe. This you can do this experiment, by the way. Here, L, the size of the system can be very big. You take some glass with milk inside, and you do this experiment, but you have it should be frozen milk. The scatter, they cannot move. They are frozen. And then you do the experiment. This is what you see. So the phase coherence length in that case is very big. Okay, so what happens now when you have those scatterers, but they move? They move, they are not frozen anymore, and you integrate over time, which means that you take, so this answers a little bit your question, but not completely. So now the scatterers, they move, and you just picture the system over bigger and bigger and bigger times, larger and larger times. So here is what you see. First, you see this speckle pattern that I showed before. And when you wait more and more, you see that this speckle picture vanishes, and you see some gray background, which is the average light intensity. So you erased this interference. You erased those interference effects, those coherent effects. Okay? So when you average over disorder, indeed, you kill coherent effect. So this is exactly the same as I said before for the Aharonov-Bohm effect. You are convinced that this is the same? Really convinced? Yes? It's not to please me. You're really convinced. Okay, so this is what happens when you average over disorder. Here you do it by integrating over time. You just erase everything. Okay.
What's your magnetic flux in this experiment?
There is no Aharonov-Bohm flux in this experiment. By the way, so here the speckle is not very beautiful. Here it is really beautiful. It is really the speckle that I showed before. This is exactly this. Okay. What is the equivalent of phi here? There is no equivalent of phi. You just have this interference picture here. This is you don't have a phi that you can change. But okay, but you see interference the same way. Okay. So disorder average erases coherent effects. So now I claim that there is an equivalent of this for the Aharonov-Bohm effect. So I'm coming back to the Aharonov-Bohm effect. Do you adjust to this gymnastic to jump from one to the other? It's not tiring? Okay. So now this is what is called the Charvin and Charvin experiment. Charvin squared is Charvin and Charvin, father and son experiment. So now I take this Aharonov-Bohm experiment of Webb, but I do the following now. So the idea of this cylinder is to do the following. Webb took one ring. And now suppose that you take another ring on top, and another one, and another one, and many, many, many rings. Okay? So you enter so it's a conductance measurement. You enter a current in this part, and you retrieve the current there, which means that if you measure the conductance, you measure the conductance through the entire system of many, many rings. In each of those rings, the disorder is different. It's a different configuration. And therefore, like this, you should average over disorder. And therefore, according to the argument that I showed before, you should erase any phi dependence, any dependence on the flux. You agree? You should agree, because this is what we saw before. Okay? And, okay, so what they took is a cylinder, in fact. A cylinder, you can see it as just a collection of rings. I said that they took the ring of Webb, and this, historically it's not true, because this experiment was done before the Webb experiment. Okay? But for our purpose, it's not very important. Okay? So you are with me. Here, in principle, there should not be any phi dependence. And indeed, the modulated signal at phi 0 disappears. So indeed, we were right. By averaging over disorder, I killed the Aronoff-Bohm effect. But the big surprise is that instead, there is another contribution, which is now modulated at phi 0 over 2. So disorder killed the Webb signal, but replaced it by something else, which is also a phi modulation, a dependence on the flux, but the periodicity is not phi 0, it's phi 0 over 2, which means you should have the same like this, but with periodicity which is at a different frequency. Not bad. So averaging over disorder, you get a phi dependence. And this is the measurement. And you see, this is the measurement of the resistance as a function of the applied flux. And you see that indeed it oscillates. Isn't it fantastic? You are sorry that you didn't hear about mesoscopic physics now? And you say, wow, this is terrible. So, by the way, here, in fact, I should say that there are two curves. There is one solid curve and one half-lines curve, dashed curve. And you see that they coincide. So one is the measurement and the other one is the theory. So those are effects that I just want to tell you, we understand them very well. We have good theory, although we don't know what is L5. Not bad? This theory of mesoscopic physics is as precise as QED today. Okay, so after all, disorder doesn't seem to erase coherent effects, but to modify them. So which means that decoherence, L phi, and disorder average are two different notions. Okay? So disorder does not kill phase coherence, it just changes it. You had a question?
What is the length of the cylinder?
The length, you want in centimeter, in few centimeters? It's much larger than L phi. L phi is of the order of 10 microns, and this is of the order of centimeter. Okay? Which means that, okay. This is second part of my answer to her, and so it will be an answer to you also.
What is a web?
Sorry?
What is a web ring?
Web is the guy, and ring is the experiment that I showed before, this ring.
Just to show a ring with a electric.
No, this was this here. This is the web ring. So this was the experiment. This is the ring. And here you inject current and you retrieve it like this. And you measure conductance. This is the web ring. Okay, so now what about speckles? So speckle patterns, we just said that if we average over disorder, we kill this interference picture. But then, if we believe what we just showed with this Aronoff-Bohm business, then we should replace those coherent effects by something else that also shows coherent, the equivalent of the phi 0 over 2 for the web. So what is this? So here, what is represented, so this is this Speckle pattern, and so those are fluctuations of the intensity, I told you, and this is the picture of the fluctuating intensity. So this measurement is just this measurement on okay, you look like this, and you see the fluctuations like this. And now you average over disorder, this, and if what I said before is true, you should get something flat, gray, uniformly gray, flat. Okay, flat as function of this is the angle, which means this is the angles here at all the directions. You're with me? And here, if I average over disorder, I should get something flat. But if there is an equivalent of this Charvin and Charvin effect, perhaps it should not be so flat. So what is the answer? You are full of suspense, like a Tarantino movie. Okay, so this is the answer. When you average over disorder, it is not flat, but there is a peak here, which is a coherent effect, because without coherence, it is flat. When you average over disorder, it remains something here, and this something is called coherent backscattering. It is the equivalent of this phi 0 over 2 Charvin and Charvin effect, but for waves. And this is a picture of this coherent backscattering of this experiment. So which means that when you average this, and when you look in the backward direction, what you see is not something that is flat, but something that has an angular behavior. So it remains a coherent effect. And this is absolutely the equivalent of zero temperature. There is no temperature here. So this is the beauty of what we're doing here. There is no temperature. We don't have to worry about this. So this effect has been observed for the first time in the University of York, in Amsterdam, and also in Grenoble. There were two back-to-back experiments. And it has been reproduced in all what calls himself a wave. And it has been a very active field in atomic physics for a while. So this, at the moment that people say, we have multiple scattering, we have waves, we have atoms, we have photons, we have whatever, we should observe something like this. Okay? And if there are charges, they will observe Charvin and Charvin effect, all this. So this is really the smoking gun proof of existence of mesoscopic effects, this coherent backscattering or Charvin and Charvin effect. Okay, so what we may conclude from all this is that elastic disorder is not related to decoherence. Disorder does not destroy phase coherence, and it does not introduce irreversibility. So I hope that this changes your view on the world. But disorder is not the bad guy. It's not a nuisance. It's even the opposite. Sorry? The disorder, what? Okay, so disorder is very good. So now, how is it possible to understand? By the way, how it's what? How much time do I have? 15 minutes? No, I can speak forever. But it's not important. It's not important. I continue. It's not. Is it too quick or it is too slow? Or I can do whatever. I can adapt myself.
Like this, we can skip the line.
No, but is it? 40 what? 40? But about the speed, is it okay? You like the movie so far? Yes? Okay, so how to understand average coherent effects? So now I'm starting to give you some theoretical tools. So I want to calculate a complex amplitude, which means that I have a wave, plane wave, that arrives on the first scatters. I have many scatters. You remember my first picture that there are billions of scattering events and all this? So now I try to build an object that describes this multiple scattering. So I have a plane wave here that starts, this is the first scatterer, and then the wave emerges from the system here along this k prime direction. And I'm interested in the complex amplitude A of k prime that is associated to the multiple scattering of a wave, electron, photon, or whatever, incident with the wave vector k and outgoing with k prime. Okay? So now, if we generalize this idea of the Young two-slit experiments that we saw before, what we know is that the total amplitude is the sum of an infinite number of amplitude paths. They are called sometimes Feynman paths, okay? So I have to calculate the amplitude for every possible sequence of multiple scattering. This is one, this is another one, this is another one, and there is a continuous family of such paths. And I have to sum all of them and to take the square of this in order to calculate an intensity, right? So this is what I have to do here because of multiple scattering. Okay, so I can write this amplitude as I told you, as this Feynman sum. So it is a sum over all R1, the first scattering events, because the first scattering event can be whatever I want, and over the last scattering event, because it can be whatever I want, times some amplitude here that I will discuss in a second, times this just this phase factor that tells you that this wave is scattered at R1, and this wave is scattered out at R2. Okay? So this is a very simple expression. Do you agree that it's a simple expression? Yes? Yes? You are with it? Now, what is f of R1, R2? It is this sum over all the possible paths of an amplitude and a phase associated to each of those passes. So it's a generalization of this Young two-slit experiment. Okay? All the notes are accessible. All this is, so you don't have to. So now what is the intensity? In order to calculate the intensity, which is what I am interested in, I have to take the square of this A, to take this squared. So this is this, okay? And just let's write it together. It is the sum of R1, R2, R3, R4, product of those amplitudes, and those phase factors. Okay, this is very simple. And this product of amplitudes is the sum over all possible passes, J, all possible passes J prime, of the products of those two amplitudes, which I can write like this, separating the amplitude and the phases. Are you with me? So now, let's see what happens when I average over disorder. When I average over disorder, what I know is that most of the contribution here disappear because the dephasing between the two trajectories is much larger than one. So I'm not sure that it's so clear what I'm saying. What is typically the phase delta J of that is written here of a given trajectory? This phase is this delta J. Basically, is up to factor 2 pi or whatever. It is the length of the trajectory, the total length. I will call it this, in units of one of the characteristic lengths that we have, which is the wavelength. Okay. And usually so this is a big phase because the length is much larger than the wavelength. But now what you see is that when I look at dephasing between two amplitudes, this is typically and this length difference usually is much larger than lambda because the two trajectories that I designed here, you see that they are much larger than lambda, which means that this dephasing is very big, and therefore the corresponding contribution here will be 0. Okay? So most of the trajectories here in this intensity, they disappear because of a very big dephasing, except those ones which corresponds to 0 dephasing, which means exactly the same trajectories. And exactly the same trajectories is this. Okay? So all those trajectories, coupled trajectories, they have 0 dephasing, and therefore they will not disappear in the intensity, so they will contribute to the intensity. Okay? So when you do something like this, what you do is what is called in all the good books, the Drude approximation. The Drude approximation is just to throw out anything that could be related to any coherence. You keep only this. Okay? So now that I have this, I could say that there is something in physics that is called the Reciprocity Theorem that is better said by, if I see you, then you see me. Okay? And this Reciprocity Theorem tells me that if this contributes, then the one where I just reverse one of the trajectories should give exactly the same. So this is what I did here. I take one of those trajectories and I reverse it, and this should contribute the same way. Right? This, if I see you, you see me. This is this. Okay? This is a theorem. It's not just a conjecture. It's a theorem. And therefore, the total average intensity, average over disorder, now this is what we're talking about, is this, and it has two terms. So it has this guy, but it has two terms here. This term is the incoherent classical term, this Drude term that you keep only this. And this term is an interference term. And this interference term is related to this reciprocity theorem. Okay? It's simple. Life is simple. Okay, so I have those two terms. But the point is that generally, this interference term disappears. Why does it disappear? It disappears because when you are summing now over R1 and R2, this is a phase, and this will also disappear on average. Okay? So Drude is right. It's not that Drude missed this term. This term usually disappears. But it disappears except what you see from the way it is written here, it disappears except for two exceptions. The first one is when k plus k prime is equal to 0, which is called backscattering, that the direction, the outgoing direction k prime is equal to minus k, so it is backscattering. We used this term before, no? A coherent backscattering. This is this. Okay, so what you see in coherent backscattering is just the fact that you have this peak for 0 angle here is because of this. Don't worry, this is the coherent backscattering. If you don't understand this graph, it's not so important. By the way, should I say that the main line here is the experiment, and the points are the theory. So it's another example where mesoscopic physics works quite well. This is usually, I wait at that point, people to say, wow, fantastic. No. So it is beautiful. Okay? And so this is this coherent backscattering that I was talking about. And the second instance where this coherent term does not vanish is when R1 is equal to R2. And this corresponds to closed trajectories. And closed trajectories is precisely this Charvin and Charvin effect, where we have those rings that, okay? So those two examples, Charvin effect and coherent backscattering, corresponds to this interference term in multiple scattering theory that remains even once after we average. Okay? It's beautiful. And this is what I discussed earlier. Okay? So all this is there. You have questions? R2 is the position of the last scattering event, yes. And you have to sum over it. But if I am in an experiment where all the first scatter and last scatter are the same because it's a ring, then I sum over R1 only. And then this interference term does not disappear. Yep.
Approximation you did with the Random phase approximation, I guess.
Yes. I was not doing any approximation. I was just saying that all the interference term disappear because of large dephasing. Okay. This is a sad fact of life. This is not an approximation. It's something that I cannot avoid. Okay? It's not an approximation. The approximation will come afterwards. Don't worry. I will tell you. Okay, so, sorry. Okay, first of all, you see that for waves, for photons in the assembly of atoms, the temperature can just influence the dynamics of the atoms, and therefore this averaging process. I showed you that if the scatters, they move, you average in your system. So temperature can trigger this, but coherent effects will remain. The coherent backscattering will remain. And for electrons, sorry? But if the coherent effects stay, can you say the system thermalized? That it thermalized? Well, no, the system can be thermalized or not. This is not very important. Temperature may play a role. It plays a role as decoherence, as the phase coherence length. But the system does not have to be at thermal equilibrium. Because, for instance, when you do an experiment of transport, conductance, your system is not at equilibrium because you put a voltage. So you could have temperature, but your system does not have to be thermalized. It has to be in a stationary regime. That's enough, but not thermalized, not necessarily. Okay, so other questions? So could you speak louder? No. Kondo effect is also part of mesoscopics, but I had to just to give few topics, so I did not discuss Kondo effect, but the Kondo effect is other thing. It has to do, for mesoscopics, in what is called quantum dots. Did you hear about quantum dots? So quantum dots are mesoscopic systems that, to some extent, can be described as a Kondo impurity. Okay, so quantum complexity. So I want to summarize a bit what I said so far. What I said is that we are considering random quantum systems. So now you could say, waves in milk, it's not quantum. I know, but it's called quantum system. So this is the terminology. Okay, but electrons, by the way, electrons also in conductors, they are quantum waves, but they are not quantum system in the sense that there is no entanglement. Entanglement for me is real quantum. When there is no entanglement, it's not quantum. It's wave mechanics. So all this is wave mechanics, but it's called random quantum system and quantum complexity. So first thing is that disorder does not break phase coherence, and it does not introduce irreversibility. Okay? We agree about this. Second thing, disorder introduces randomness and complexity, which means, what I mean by this is that all symmetries are lost and there are no good quantum numbers. This is the meaning of what happens with disorder. So I will give you an example. If you look at this system, which is the diffraction by a circular aperture, you see an interference picture, right? But this is an interference picture full time. And the beauty of this interference picture is that you can label each of the rings, interference ring, by an integer or a set of integers, okay? And you are happy, you call it quantum numbers. They are the same quantum numbers than for the hydrogen atom, if you want. The same idea. You can label the interference picture, right? Now this is also an interference picture at exactly the same level. The only thing is that you cannot label the interference here. There is no set of integers or whatever that you can use, that you can design in order to label this interference picture. So this is not less interfering or coherent than this one. The only thing is that when you go to coherent multiple scattering, you lose all the good quantum numbers. You lose the possibility to label a picture, an interference picture, using integers, using numbers. Okay, this is what is called quantum complexity. Okay, for instance, if you take so there is an example that you may know here. If you take a particle, a quantum particle wave, okay, in such a stadium square, you can solve the Schrödinger equation and get just all the energy levels and all the wave functions using two integers, right? But if now, instead of this, I take a billiard like this, okay, you cannot do this. It's not that quantum particles here is less coherent than here. Here it is chaotic, so you cannot label with two integers or three or whatever, because it is chaotic, and here you can. But this is the same physics. So here it's the same, okay? You know how this billiard is called? Do I know? Yes, it's a Bunimovich billiard, I think, right? Sinai billiard. Sinai billiard. Sinai billiard. So this is not integrable, but this is integrable, but it's the same physics. So here it's the same in our problem. And so this is the idea. Mesoscopic quantum systems are complex systems. And in fact, almost all quantum systems, except the hydrogen atom perhaps, are complex quantum systems. So this is why it's so important to be able to track coherent effects, although you don't have good quantum numbers. Complexity, which means randomness here, and decoherence are separate and independent notions. You can be complex quantum systems, but fully coherent. That's what I just discussed before. Complexity is the loss of symmetries or of all the good quantum numbers. And decoherence is an irreversible loss of quantum coherence that occurs when the size of the system is larger than L phi. So there are two different notions. Okay? So this is all what I wanted to tell you here. And a mesoscopic quantum system is a coherent complex system, quantum system, with L smaller than L phi. And again, most of the quantum systems are like this. And if they lost their coherence, then they are classical systems. We are not very interested. I mean, we're interested, but there are other people interested in them. And if they are quantum systems, then they are coherent, but they are complex. Again, now, if you are interested in real, not second quantized, how it's called? Aspect calls it, how? Second revolution, quantum revolution. If you have a system with entanglement, entanglement is not killed by all disorder or whatever. You can have entanglement the same way. It's fully coherent. Is it sane to at 12:30 to speak about entanglement. I see people saying, you know, leave me with entanglement. I want to eat something. I need some proteins. Okay, so this is the idea, the definition of mesoscopic quantum system. It's a quantum system that is complex, but that is fully coherent. And you see again, there are many systems like this, not only in condensed matter physics, not only in atomic physics. An example. Yeah, it's almost the end of what I wanted to say today. And I have 10 minutes, 20, 15 minutes?
15 minutes.
Okay, that's very good. This is what I wanted to. So I told you that if we have complex mesoscopic systems, then apparently it is not self-averaging. You remember when I said that if you measure the resistance of this piece of copper, there's no copper inside, but of this piece or this one, we get the same. And this means that the conductance classically at the macroscopic level, when it is incoherent, is self-averaging. We do not see any fluctuations of the conductance, okay? So this is the classical limit where L, the size of the system, is much larger than L phi. So L phi is much smaller than this size, okay? So in this limit, I can cut my systems into a collection of n equals to L divided by L phi to the power d. D is the space dimension, 1, 2, 3, okay? Much larger than 1, statistically independent subsystems, okay? If I have an incoherent system, I can just say that it's a juxtaposition of many incoherent systems, okay? Classically. You are with me? So now, what does it mean? It means that a macroscopic observable, like the conductance, defined in each subsystem, takes independent random values in each of the n pieces of my collection, and the law of large numbers tells us that any macroscopic observable is equal with probability 1 to its average value. So this is exactly a phrasing of saying that if I take a piece of each of these, I measure exactly the same. It is self-averaging, okay? I measure only one value. I don't see any fluctuations. This is a classical result, classical in the sense of non-quantum, okay? So the system performs an average over realizations of the disorder. Now, if L is smaller than L phi, this is not true. The system cannot be self-averaging, and we expect deviations from self-averaging, which reflects the underlying quantum coherence. Yes? So what do we need for this? We need first a good understanding of the phase coherence length, but then I said that we don't have it. But anyway, sometimes we have it. And a description of fluctuations and coherence in the quantum complex systems. Okay, so I will give you an example now. An example that you know, that I mentioned already several times today, the electrical conductance of a metal. Now, no Aharonov-Bohm effect, nothing. Good old metal. A metal can be modeled as a quantum gas of electrons scattered by elastic disorder. This you agree? This is this Drude. And I need elastic disorder because I know, you know that if there is no scattering, then the conductivity is infinite. Then I need this. And at T equal to 0, 0 temperature now, in the absence of decoherence, it is a complex quantum system. Right? So now, due to disorder, there is a finite conductance, just what I said, which is a quantum observable, this conductance. And classically, the conductance of a cubic sample of volume L to the D is given by Ohm's law, which is what is written here, that the conductance is the conductivity times the size of the system to the power D minus 2. So you know this is Ohm's law. Do you recognize Ohm's law here? Who doesn't recognize Ohm's law here? Everybody recognize Ohm's law here? Beautiful. First time I saw it, I did not recognize. So. Okay, so it depends on the dimension of the system, so this is what it is. Okay. So now, classically, what does it mean that that the conductance is self-averaging? It means that the relative fluctuations of the conductance, which is defined here, delta G is just the variance of the conductance divided by the average conductance over disorder, which is just this Ohm's law. This should behave like 1 over n, and according to what we said, this is the classical limit. It is L phi divided by L to the power d over 2. Okay? So this is how the relative fluctuations behave. And this means that the variance of the conductance, if you just replace it here, it goes like L to the power d minus 4. Do you see it? You don't see it? You want me to add one line? So what did we obtain? We obtained that delta G divided by G average goes like 1 over L to the power d over 2. Okay? And G average goes like L to the d minus 2. So this should imply that delta G squared should go like G squared times L to the d. And this should go like L to the 2d minus 4 plus, but this is 2 like this, plus d. Where is the mistake? Times, so this is a minus here, and this is a minus here, because it was 1 over L, and this goes like L to the power d minus 4. And this is what is written here. So this means that in 3 dimensions, the fluctuations, the variance of the conductance goes like 1 over L, and for a very big system, it goes to 0. And this is the fact that classically, the conductance is self-averaging. Okay? Now, in mesoscopic quantum systems, what we will see tomorrow is that the variance, delta G, is independent on the size of the system. It is just a constant, E squared over H. E squared is the charge of electrons, and H is the Planck constant. And this is just what it is. So it is independent of the size of the system, which means that even for a very, very big system, but coherent, smaller than L phi, the fluctuation of the conductance does not go to 0. So which means that all the arguments that if I measure the conductance of this quantum wire or that quantum wire, I get the same, is not true at the quantum level when we are coherent. Okay? Did you got this point? Again, who did not understand this point? Who didn't understand? So there is one that sleeps completely. So, okay. So now those fluctuations are quantum. They are large, over the 1, E squared over H. Independent of the source of disorder, they are called universal. They do not depend even on the disorder, on the elastic mean free path. They're just constant. E squared over H. They depend on nothing. Isn't it beautiful? And so in the mesoscopic limit, electrical conductance is not self-averaging. And here is just experimental proof of this. What I put here is a collection of conductance obtained. This is the conductance in units of E squared over H as a function of a magnetic field, just to see the fluctuations, for 3 different systems. One system is a ring of gold. Another system is a semiconducting system, is a MOSFET of silicium. And the third one is the numerics of the Anderson model, the one that gives this famous Anderson localization. And what you see here is that the average value of the conductance, the average conductance, is very different. Here it's of the order of, say, 1,000. Here it's of the order of 10. Here it is of the order of 1. But the fluctuations, which means the width of the variations here, you see that here it is of the order 1, here it is of the order 1, here it is of the order 1. In fact, it is 1 in units of E squared over h. So those are these universal conductance fluctuations, that the width of the fluctuations is universal of order 1 and does not depend on the size, does not depend on the type of system, either gold ring, MOSFET, or numerics on a completely different model. Nice? So that's the end. So you woke up precisely at the good moment, so this is the end. I think. Let me see. Yes. Okay, so thank you very much. You may have questions. There is something I wanted to say also. You were told that I'm supposed to give a colloquium on the day after tomorrow, right? So you may think that I'm an aficionado of the mesoscopic physics, which is true, but the colloquium will be on a completely different subject. It will be on graphene, fractals, and a bit of topology. So absolutely zero overlap with all what I'm saying here. So if you think that coming to the colloquium you will understand more what I'm talking here, it's a big mistake. It's what I wanted to say. Questions? Yes. I talked about what? Metals, yes. To the quantum Hall effect? Oh, yeah. Yes, absolutely. Quantum Hall effect is so the question is what I've been discussing today related to, in any sense, to the quantum Hall effect, right? That's what the question. So the quantum Hall effect is indeed a mesoscopic effect. In many instances. First of all, it has to be a mesoscopic system. It has to be smaller than L5 and everything. The conductance is quantized in units of E squared over h, precisely like those universal conductance fluctuations. The physics, the difference is that for the Hall effect, you need a strong magnetic field, whereas here, the magnetic field that I considered are Aharonov-Bohm flux, so the magnetic field is 0. And the point is that when you merge together the effect of disorder and effect of a strong magnetic field, you get yet another field of physics, because strong magnetic field wants to build Landau levels. Disorder doesn't want to build Landau levels, and they clash together. And the way to solve this clash is to create edge states, edge currents, because all the states are localized in the bulk of the system, and the edge currents gives this E squared over h topological conductance. Fantastic. It's really fantastic. I really think so. Yep. I gave you a few examples. For instance, if you think of electrons, coupling to phonons is a source of decoherence. Decoherence, you can think of it as broadening of the energy levels. So this imaginary part to the energy that you give. Okay. Another source is coupling to chaotic degrees of freedom. So there are electron-electron interactions. They are a source of decoherence. And you can design many like this. Absorption is not a source of decoherence, for instance. If you eat photons, your system eats photons, but the remaining photons are coherent. You will see less signal, but the signal will be always coherent. So absorption is not, but inelastic scattering, like scattering on phonons, on electrons, and all this is source of decoherence. But for instance, just to entertain you a bit, there were a number of people that thought at the beginning that the ultimate source of decoherence was the fluctuation of the quantum vacuum. And then the electrons are related to this, and this is what limits their coherence. And there were even experiments done in that direction. But we don't know. We don't know yet. We can identify a few, but not all.
I understood that the fluctuations are independent of the system, what you said with this theorem. So the size of the fluctuation you said is around 1 in each of these. But because you are taking the average, but if I take a different sample, the fluctuations will have the same width, but this curve will be different?
No. Okay, sorry. So I did not explain properly what is this curve. For each value of B, it's like a new sample. Here you see, this is the conductance. It's not average conductance. This is conductance. For each value of B, how do I'm doing this? Don't ask for the moment. Each value of B here, it's not Aharonov-Bohm flux. It's something different. It's like having a different sample. Okay? So what you see here is conductance. Each B is one configuration, and you see that the average typical, is around 880. So this will be the average, but the width of this distribution is of order 1. So this is for each B is a realization here also. Okay, but it's a completely different system. So here you see that. The conductance fluctuates for each value of B, but the average, so the average changes very much, but the width of the fluctuation is of order 1. Now, if you ask, how is it possible to change configuration by changing B? This is like her question. I will not tell now. I will tell later. Because then usually the question that comes afterwards is it ergodic, an ergodic way to change configurations? And the answer is no, but yet it's a good way to, but it does not have any incidence on what I'm saying, but it's not ergodic. This was your question. Yes? Okay, so here, each B is a different configuration. Other question or no? Herr Chairman, so.